Welcome back. We are continuing with applications of ring embedding and extension, and today we have the following problem. Given any ring R, then R can be embedded in a ring S such that S with identity and has the same characteristic as the ring R. The proof is going to be really short because some parts of the proof are very similar to the proof of the theorem in the first session, which is called Doro extension theorem. And if you recall, we proved that any ring R can be embedded in a ring S, where S is constructed as R cross the ring of integers. And R is embedded as an ideal, which is R cross the element 0. Okay? So the first attempt into the solution is to try to use this same construction. So we let S equal R cross Z, and let's see if this works. Okay, so assume first that the characteristic of R is 0. Okay, now we want to see if the characteristic is S is going to be also a 0. So we let characteristic of S equal N. Okay, remember that the characteristic of a ring is the least positive integer N such that N times any element R in the ring equals 0. And this here means R added N times. Okay, but if the ring is with identity, this is equivalent to N, the identity element of the ring equals 0. Okay, so the identity element added or summed N times must equal 0. Okay, this is an equivalent definition of the characteristic. Now, characteristic of S equal N, this implies that N into the identity element of S, which is a 0 of R, of course, and 1 of the ring of integers. So this is the identity of Z, and this is the identity, this is the 0 of R. Okay, this equal 0 into N 1Z. Okay, and this must equal, of course, 0 and 0. Okay, this is a 0 of Z and this is a 0 of R. But this is possible if and only if N 1Z equals 0. Okay, and this is possible if and only if N equals 0. So in this case, we conclude that characteristic of R equal the characteristic of S if it is 0. Okay, now assume that characteristic of R equal M, which is an integer greater than 0. Okay, now this implies that M into 0 1Z equal 0 M 1Z. Okay, and this must equal 0 and 0. Okay, but this is possible if and only if M 1Z equals 0, which is possible if and only if M equals 0, a contradiction because M must be greater than 0. So this ring S here, by this definition, is not suitable. Okay, it works only for characteristic R equal 0. Now what is the solution? If the characteristic is M, then we, instead of S equal R cross Z, we take R with a Cartesian product of Zm, okay, Z sub M, the ring of integers modulo M, and then R to be embedded with R cross the 0 of the ring of integers modulo M, okay. So in this construction, of course, it needs to be proved that S equal R cross Z sub M is a ring. Needs to be proved that it is a ring. But the proof is very similar to the proof we have done for R cross Z. Okay? So S equal R cross Z sub M. This is a set of all elements A and K. But K here is an equivalence class. Okay? Is an equivalence class. Is all the non-negative integers congruent to K mod M, okay? Such that, of course, A in R and K bar is in Z sub M, okay? Now, what are the operations? The operations are very similar to our construction of R cross Z, okay? So addition and multiplication are defined as follows. Addition A and K bar plus B with some L bar, this equal A plus B, and the second component K plus L all bar, and the multiplication of the order pair AK bar with B L bar equal AB, so the first two components, plus L into A, so this is A added L times, plus K B, and the second component is KL all bar, okay. Now as you can see, this is exactly the same addition and multiplication we defined on R cross Z, except that we are using here equivalence classes in the ring Z sub M instead of only integers. And exactly in the same way, it can be proven that these two operations are well defined, and all the steps of proving that S is a ring follows similar methods. Now, so from that theorem, Doric extension theorem, following the same methods, we conclude that S with the above operations is a ring with identity 0, of course 0 R, and the 1 of Z sub M, okay? This is the multiplicative identity. Now let's check the characteristic. We have characteristic of R, we assumed it to be equal M, and I do not need M to be greater than 0. It can even be 0, okay? Now in the ring Z modulo M, it is always true that the characteristic of Z sub M is also M. This is by the very definition of this ring. Now, what is the characteristic of S? Okay, if we take M and we take the identity added M times, then we have M 0R comma 1 sub Zm. Okay, this equal M0 and M1 Zm. Okay, and this equal, of course, 0 of R, and this is the characteristic of Z sub M. So this is the 0 bar. Okay, so this implies that the characteristic of S equal M. Okay, so it holds. I do not even need to test it with the identity element. It also works easily with any element of S. So M into A and K bar equal MA MK bar, and this equal the 0 of R, and we said this is the characteristic of Z sub M, so this must be 0 bar. So also characteristic of S equal M. Okay, so we completed this proof that any ring R can be embedded in a ring S such that S with identity and S has the same characteristic as R. We continue in the next session with further applications on ring embedding and extensions.